Yes, yes, yes.
All right. Okay. I have to share a screen first. Okay, I'll share my screen, full screen share. Can you see my screen? Yes?
Yes, 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 yes.
All right. Okay, I'm going to put, this is a slide presentation. Okay, so you still see my screen? Loopholes, which are the contextuality loophole and the correlation, correlation in background fields. And I'm going to show how these two loopholes are related. And it's good. I think it's good news because if you close one of the two, or you think one of the two is closed, the other one is closed as well. So this simplifies things. I will be very brief, but I want to just to set the historical line, recall how all this started. And I want to recall the paper by Einstein, Podolsky, and Rosen in 1935, where they wanted to prove that quantum mechanics was not a complete theory. And for that purpose, they proposed an experiment to show that you could overcome the principle of uncertainty, which is the pillar of quantum mechanics. So they proposed an experiment with two entangled particles, the first and the second particle going through, you entangled them by letting them going through a double slit. And then you can measure the position of the first particle, which, assuming that is a local measurement, you are not affecting the second particle. And from the fact that these two particles are entangled and you know the difference between their distances, you can compute the distance of the second particle without intervening this particle at all. Let's do this experiment once again, but instead of measuring the position of the first particle, we measure the momentum of the first particle. And again, because we are not affecting the second particle and we know that they are entangled, we can compute the momentum of the second particle. So they said, I can compute the position and the momentum of the second particle without touching the second particle, and I have overcome the uncertainty principle. So if I assume that quantum mechanics is complete and then I can overcome the uncertainty principles, I run into a contradiction, and they conclude in their paper that quantum mechanics is not complete. And they only have to assume two things: that when you act on one particle, they are sufficiently far away, you do not affect the other locality. And they provide a definition of realism, which is here my main concern, which says that you can measure something is real if you can measure it without disturbing the system. So you can attack locality or realism in local realism, and I want to attack realism as defined by Einstein. But I was not the first who attacked their definition of realism, because Bohr in the same year, 1935, only 5 months later, he found a mistake in his reasoning. And what he introduced, apart from the principle of complementarity, which was introduced in this paper, he also introduced the concept. He did not say it explicitly, but he was introducing contextuality here. And what Bohr realized is that when you measure the position of the first particle, you have to use a slit that is attached to the same table. Then the particle goes through the slit, transfers some momentum in terms of electromagnetic radiation, but you can locate the particle because it's fixed. But when you measure the momentum of the first particle, you are doing a different experiment. It's a different context because the slit cannot be attached to the table, the same table, because you need the particle to transfer the momentum to the slit, and from this momentum transfer, you measure the momentum of the first particle, but you know the slit moves, and now the particle cannot be localized. This is the uncertainty principle. So there are two experimental contexts. And Bohr is very aware in this paper that you are not measuring something possessed by the particle. It's not that the property was possessed by the particle before. You are producing, through an interaction between the apparatus and the particle, the result of the experiment. So you don't measure, the properties are not real before measurement. You produce them, you create results through the measurement process. Okay. All right. But then, and I'm very happy with this, but then 30 years later, Bell, he was very inspired by the hidden variable theory proposed by David Bohm in 1952, which could explain the quantum theory perfectly, but had the property of being non-local. And then he thought that perhaps he could demonstrate that there is no local theory classical theory that can produce the results, underlying theory from which quantum mechanics would be an emergent theory from which you can derive the results of quantum mechanics. And so if you renounce to locality, of course, you are just saying that there is an action in distance. So we have this terrible action in distance coming back, which was put by Newton in the first place with his Newtonian mechanics. And the idea is that when you measure one particle far away, some kilometers away, the other particle suddenly collapses. Okay, you cannot use this perhaps to transmit information, but there is an action distance in quantum mechanics. That's the idea. This has problems with relativity principle. At least it's not easy to think both of them at the same time. All right, so very briefly again, the idea, I want to talk about hidden variable theories. Perhaps you do not want to talk about it, but I want to talk because I think that quantum mechanics does not represent the apparatuses, neither the electromagnetic background fields. So there are hidden things, of course there are. And my point is that you can use these hidden things to explain them. More stuff. So the idea of a hidden variable theory is just like the metaphor is thermodynamics. Boltzmann showed that you can obtain the results of thermodynamics from averages from the microscopic particles in the theory of Newtonian mechanics. So all the thermodynamic properties emerge from the averages by making just averages from the properties of the particles. So here is the same idea. Quantum mechanics is not fundamental. It's an emergent theory, and it's all its predictions in terms of averages and correlations and higher order moments must come from the hidden variables through statistical averaging. So in principle, it's a very clear idea, and it deserves attention. So to prove his theorem, Bell and also his advocates, well, Bell started using an experiment a little bit different from Einstein, Podolsky, and Rosen, and it's an experiment proposed by Bohm and Aronoff in 1957. And instead of position and momentum, they used the spin, the internal angular momentum of the particles. So the idea is that you have a beam of particles, you have a Stenger-Lach apparatuses with a non-uniform magnetic field, and then the particle interacts with the magnetic field, and then it can go up or it can go down. And so the experiment is just you have a source, you know, all of you know the experiment very well. Let's say you have some pion zero particle, it integrates, and then you have two entangled particles through their spin. They are in an entangled quantum state, flying apart each other towards the respective Stenger-Lach apparatuses. You can orientate the Stenger-Lach apparatuses differently, and you can compute the correlations of the combined product of the spins of both particles in quantum mechanics, and you get these famous results. So the idea of Bell is that if you try to do this with some classical theory, underlying theory, you cannot explain these correlations. That's the whole idea. No? Okay, I'm going to use the last, the version of the theorem, which is the most modern one, which is the one which has the least number of assumptions, but there are some assumptions here, and I want to discuss if these assumptions are good for field theories. And my proposal is that so two of them are not completely correct, and you can modify them, but you must make assumptions to derive. The whole idea is that if you want to derive the CHS-H-Bell inequality in field theories, you need to make further assumptions beyond these four. So, well, in principle, we assume that the hidden variables are whatever you want. Fields is the most complicated thing in classical theories you can think of. Function, there exists a function which is the result of measuring the spin. A function which is the result of measuring the spin. Here, Alice, if you want, measures the spin of one particle, and this function depends on some hidden data, and this hidden data, it's always believed that this data correspond to the source, and I'm going to show that you cannot only use in field theories data from the source. Okay, you have to put here the fields, the background fields all over the initial Cauchy surface. So this property, if you only refer to hidden variables at the source, is wrong. I mean, in field theories, you need more information from the background fields to propagate the initial conditions. And also, it is assumed that there exists a probability measure. Again, if you think that this probability measure does not involve the apparatuses, that only involve hidden variables at the source, you are wrong. You cannot obtain all the information from the particles. You need, but because the background fields are playing an active role, they are contextual fields all the time, fueling the Zitterbewegung. Well, anyway, these two properties are the properties I'm concerned with. I will assume locality. I don't want to go into non-local stuff. I don't believe in action distance. So basically, you can express the measurement of a spin by Alice without saying anything about the, just by specifying the orientation of the apparatus of that Stenger-like apparatus and not the other one. So both Stenger-like apparatus, you don't need to cross them here in the measurement of the spins. So there is no dependence on B here, no dependence on A here. I assume that's correct. So, okay, the theorem, the inequality of Closser, Horn, Simony, and Holtz, basically is this inequality. You can use two different orientations for each Stenger-like apparatus and combine then the correlations to produce this inequality. This can be done as long as you assume this hidden variable integral. And these two statements are implied. Each other implies. This was demonstrated in a paper in 1982 by Arthur Fine. He proves that if this holds, this holds. And if this holds, this holds. So this is necessary and sufficient condition. So if one of these two does not hold, then the other does not hold as well. And I want to show that the first one here does not hold unless you make assumptions on background fields. That's my point. Well, not my point, it's Morgan's point. I just connect this to contextuality. So quantum mechanics violates this inequality, and it is believed that classical field theories obey this integral, so you can, classical field theories cannot violate this inequality, but you have to make further assumptions. Okay, so the first thing, because I'm going to introduce contextuality, and people usually mix. This happens in some papers also of Marian, they mix times. So you have two different times and you have to connect these times. The first time is the time of measurement, if you want, or well, that's the second time, the latest time. That's when you measure correlations. Correlations are not measured in the beginning, it's just when the particles arrive at the apparatus. So strictly speaking, your correlation function must be computed with the probability density at the time of measurement. And the hidden variables appearing there is the particles hidden variables, and also the apparatuses hidden variables, because you have the magnetic field of the Stenger-like apparatuses, but that's at the time of measurement. So what you have is a probability density evolving in a space-time, which you have a stochastic process if you want, and you have a measure on a set of events. And moreover, this probability density at the time of measurement is contextual. It depends at the time of measurement on the apparatuses. Because if you change the orientation of one of the two Stenger-like apparatuses, this probability density is going to change. The interaction between the particle and the apparatus is different. All right. So you cannot avoid here in this, at the time of measurement, I insist, the dependence in the probability density of the orientation of the apparatuses. So now the question is, can we go back to the source and forget about this dependence, about putting in the probability density this orientation of the apparatuses? And you can if you make certain assumptions. Okay, first I'm going to show that in a Newtonian-like theory, which is what everybody has in mind. I mean, people don't worry about fields very, very often. So if you don't worry about fields and you think that properties are coded in the particles, if you really assume that, you can do the inversion. You just have a Newtonian-like theory. The spin is possessed, a property possessed by the particle, if you want, from the very beginning. You don't need contextual fields. And in that case, you just need the flow. You have some initial conditions in position of momentum or spin, whatever, in the particles of the hidden variables. You evolve them through like in differential geometry by a flow, and then you obtain the hidden variables at the time of measurement. So you can backward propagate the flow, and you make a change of variables in the hidden variables through this integral, and you obtain the desired integral correlation with the one which allows you to derive CHS-H-Bell inequality, or, well, with another assumption, Bell inequality original Bell as well. But when you put fields, things are different. And I will show in what sense. So this is, again, the integral at the time of measurement. This is the fields in some region where the particle rests I mean, you can assume that particles are extended objects, or if you want points, you can assume they are points, but I put some functional integrals because I can assume some very little region where the particle is. And here I have the fields right at the time of measurement still. And of course, you have a dependence on the orientation at the time of measurement. And now in partial differential equations, because you have to take into account the evolution of the fields, the contextual fields. So if you want to find out the fields of the particle here, you need to specify at the beginning, when you set the source, all the fields in the causal past light cone in the Cauchy surface. Okay, I'm going to suppose a linear theory just for simplicity, because you can use a Green's function and you have a propagator, but you don't need it. You only need to use Cauchy-Kovalevskaya theorem of uniqueness and existence of solutions, and it is guaranteed that if you have this initial data in this past light cone at the beginning, then you can obtain the value of the fields at the time of measurement. Okay, so let's see if we can backward propagate to the source now and what happens. So when you do that, the problem is, okay, forget about the gray region. You have Alice. This is where the particle is measured inside the Stern-Gerlach apparatus. This is where Bob measures the spin inside, if you want the other Stern-Gerlach apparatuses. These are the world lines of the particles. This is the source where they are emitted, but you need all the information to obtain the result in the entire causal past cone at time 0, where the particles are created at the source. And the problem is that now that the apparatuses are inside these light cones, okay? So in principle, when you revert the flow to get the initial data, you cannot avoid a dependence on A and B, not for the moment. We will discuss if you can avoid it or not. But in principle, you cannot avoid it because you have the apparatus here, all right? And these fields, it's not just the apparatus, it's the fields in between the apparatus and the source. There are fields, background fields fluctuations all over in the entire. So you need these fluctuations. They are traveling through the electrovacuum. Okay, so in which case can you neglect or avoid this dependence? So here is what you need to assume: two things. And these two things are explained in a very amazing, brilliant, I think this is a very brilliant paper. It's not very cited because people in Bell world, they don't really care in general about fields as far as I have read. Not truly care about fields, all the details of fields. But this guy really cared about it. And he said that there was an enclosed loophole. He called the correlation loophole. What he's saying is, if you want to go from this probability density, define all over the past causal past initial hidden field data, you need further assumptions. So let me be brief and concise. This is the past cone, the red region of Alice. This is the past cone of Bob in the initial data. I'm going to define the intersection where the source is between both initial past light cones, and I'm going to call this sigma C. I'm going to define the region of the past light cone of Alice that does not intersect with the past light cone of Bob as sigma A, and I'm going to define by the same rule this region sigma B, where you have all the initial fields except the intersection with Alice. And you have these three regions: this region for Alice, this region for both, and this region for Bob. So in this case, if you assume, you have to assume two things. I think one of them is quite reasonable, and the other one, it must be proved, and it's not easy to prove at all. You must assume that the probability density, or if you want the fields here, all over the region sigma A are uncorrelated to all the fields in region sigma B. And if you guarantee this, you can separate both. And then if you also assume that the probability density of where the source is does not depend on A and B, which is very reasonable, I think, because otherwise you would get a super determinism in the original sense of Bell. I will say some more words now. If you assume this, if this holds, you can derive the CHS H-Bell theorem. But if you don't have uncorrelated fields here and here, or here and here, you have to prove that all over this region and all over the region they are uncorrelated. You cannot derive the CHS H-Bell theorem. Some people would say, well, this is some other kind of super determinism. In some sense, you could say yes, but it's not the original one. I'm not saying that the fields of the source are correlated with the orientation of the apparatuses. No, it's not the fields of the source. It is the fields outside in this light cone in sigma A and sigma B, and that's different. If you want to call that some kind of revised superdeterminism, okay, I think it's a misnomer, because I'm going to show you that you don't need determinism at all. And if you don't need determinism, it would be quite weird that you need superdeterminism, but I don't like this word anyway. But okay, because if you are deterministic, you don't have to worry about super deterministic. But whatever, I understand. I would call this conspiracy. That's how it was called also by Bell, and how Morgan calls it. This does not depend on A and B. This I can assume quite good. But that these are uncorrelated, that's saying too much. It doesn't hold in quantum electrodynamics. And I don't think it holds easily, but you have to prove it experimentally. It's a loophole. And it's connected to the contextual loophole. I've shown that. It's just Green's function connecting both of them. Okay. So if you want to assume that your apparatuses are dynamical, and you set them in flight, last instant choices, and you want to assume randomness, whatever, it's the same story. If you want to put randomness, okay, you put some Langevin current here in your, and you get a stochastic partial differential equation. You have a Langevin force, and you have just stochastic fields. Yeah, okay, that's fine. But still, you have the same problem. And the problem is that when you put the apparatus A and the apparatus B, even if you did last instant random choice, when you compute the correlation integral for these two values, A and B, you are choosing from the initial hidden data in the Cauchy surface a part of the whole ensemble of the sample space. You are selecting, you are restricting your original sample space to this situation. So it's going to appear A and B here, and the same problem is gonna be here. So you can use also stochastic field theories. I don't mind. The mustache of Langevin is bigger than the mustache of aspects, and I can cover also stochastic field theories. Doesn't matter. You have the same problem. You need to guarantee. In fact, Morgan paper is about random fields, but I don't believe in randomness. I come from chaos theory, so I think randomness is a redundant concept for me. Anyway, how do you close this loophole? Well, well, in principle, you just have to measure all the background fluctuations in this region. If you have photon experimental aspect, I mean, I would see very, very hard to close the loophole, because all the background field fluctuations here, you have to measure them somehow and prove that they are uncorrelated to the background field fluctuations. And these regions, you know, photons travel at the speed of light, so it's the fastest you can go. So the intersection region is just going to be the photons. So these fields will be correlated with this one. So I don't think experiments with photons are very good to close the correlation loophole, but I don't know, perhaps some experimentalist has better ideas than I do. But from the theoretical diagrams, space-time diagrams, I cannot tell. This is a really good setting. I would use instead to try to better close this loophole, also, although you still would have to measure background fluctuations. Fermions, like I showed before, the EPRB experiment, and they would have to be relativistic electrons at half the speed of light above. So this region is maximized. And in this way, you avoid the problem of having correlations between this region and this region. If this is 3 kilometers away, it would be hard for me to assume that this is correlated, the background fluctuations, with these. Anyway, if you want to be rigorous, you would have to prove that this isn't correlated with this. So the loophole would persist, although I would be quite satisfied if you proved in this kind of experiment with fermions have the speed of light, that there are violations of the Bell inequalities. But it's really, really hard to measure background fluctuations. There are experiments. I found some beautiful experiments here. There's an experiment to measure background, but you have to use lots of apparatuses, and you are going to distort the background fields quite a lot. I don't know if you put here an experiment to measure the background fields, you are going to destroy entanglement, in my opinion. But I don't know. That's it's not easy to close this loophole, as I see it, at least. So finally, to conclude I will say a few words on how I see from a reasonable perspective what entanglement can be. And well, in other talks, I've shown that how extended electromagnetic objects can have Zitterbewegung. I have also shown in other papers that perhaps background fluctuations are also required to sustain this oscillation. It's a very nonlinear oscillation. It is called self-oscillation. And I have derived it from the memory in Liénard-Becker potentials in classical field theories. So it is very well known in the world of nonlinear dynamics that if you have two nonlinear oscillators and you couple them, and here you have a background field that allows to couple them, they can synchronize. So you have two particles and they can synchronize in synchrony. And if this happens, whenever you measure one, the other can be anti-correlated with the other. This can happen if there is synchronization. So why do I think that background fields are important? The reason why I want to say this is because if the background fields are totally uncorrelated, it is quite likely that these particles are going to lose their synchrony, and then you are going to produce a decoherence of the entangled state. So my point of view of entanglement is that entanglement is just synchronization. It's a nonlinear dynamical phenomenon coming from the oscillation of the particles. And this was already found in clocks by Christian Huygens in the 17th century. And that's the only way I can picture. Of course, perhaps we don't need to picture, but I still think there is something there. Finally, I would like also to say a few words about Zitterbewegung, because I used Maxwell theory to derive self-oscillation, but in a more fundamental theory, particles must come from fields. And you know, if you want to have, when the two particles start at the source, they leave the source and they are, their spin, their angular momentum internal must be oscillating very, very dramatically. And it must be because I think the shape, even the shape, it's not just that particles are extended, the shape is evolving. Because if their shape does not change, you cannot get two options, up and down spin. To get two options, you need that the shape of the particle changes. If you have a rigid magnet, if you put a field, then you have only one stable direction and one that is unstable. But if you get both attractors as possibilities in a dynamical system, that means that the shape of the particle must be changing. So I think the particles are oscillons, and that these oscillons are producing background radiation. And this, well, I found this beautiful paper I read a week ago about oscillons and quasi-breathers. So perhaps you people are very interested in soliton models. Perhaps oscillons and quasi-breathers can produce this Zither. And I think also it depends on background fluctuations anyway. I don't know really how in this case, because I don't know if an oscillon can absorb fluctuations from the environment, but there is an interaction with the environment. So my conclusions is that quantum mechanics is incomplete. And the reason is that it does not represent contextual electromagnetic fields, fluctations, and it does not represent the apparatuses. Quantum electrodynamics, which is much better theory than quantum mechanics, does represent the background fields, but not the apparatuses, so it's still incomplete. And my conclusion, this is Henry Casimir, is that because there are background fluctuations in the context, is that local classical field theories do not comply with the principle of local realism, because they are contextual. The particles are interacting with their environment. They are not isolated particles traveling in nothingness. They are going through the vacuum, and the vacuum is alive. So particles are dissipative dynamical structures interacting with their environment. No isolation, that was already said by Mark Fleury, and that's my point of view, and that's all that I had to say. Half an hour